Okay, guys, let's start. Oh, Mark, in this week, you saw several different situations, and we try put a lot of focus in three main areas. That's sound, vibration, and vision. In general, we do this because those are three areas that we can find everywhere, and they have all those three areas have unique situations. That was because Professor Vijay and Brian, all the speeches talk a lot about that, about those areas. But of course, those three areas that has several sensors associated with that, but not all of them. It's in this segment, as you saw yesterday, in the sensors presentation. But today, as you saw, a lot of about sound and vision with Brian last Tuesday. The idea today is talk more about vibration to finish these three areas of study. Okay, perfect. We'll start with the motion classification. Okay, the best thing to do to talk about motion classification. Let me, try to connect with the real use of that. For example, suppose that we have you need to study a case. For example, how are the mechanical stresses in transportation? Okay, for example, if you have a container, this is a small container, and suppose I need to put goods here and transport this container all over the world. You are seeing today a lot of problems with container transportation that we're facing because the pandemic time. Well, what we have is when you have a package to transport, you usually what we can see. We can see, for example, situations where the container or your good is in a idle position, is stopped in a store, for example. But in some cases, you need to transport, to take this good or this container and by truck or by rail. You have movements in terrestrial or rail situations. I can have, for example, when we handle this kind of container, you can use forklift, for example, to go up and down with this goods, or you can have a ship. When you have a ship, the situation is much more complex. You can imagine you have a container in a ship. In case of ship, you can do a lot of things with the ship. We'll talk more about that. So if you think about to study how the stress happens when you transport some kind of goods, the idea is to let's define some class to do this study. So you define, I want to see how this happens in maritime way, how this happens in terrestrial or rail, we will put it all together, how we use a forklift, and how I can say that this good is stopped or idle, doing nothing in the store, for example. How we do that? Well, as every one of the projects that we did this week, and since Professor Vijay explained last Monday, we need to follow machine learning workflow, correct? And Brian put a lot of focus in this last Friday. When I do that, we should collect the data. Usually need to pre-process the data. You saw an example when Brian showed that the sound need to be transformed to image to be better classified by the model, correct? And you need do all the training that we do in the cloud, let's say, with a lot of data, a lot of machine power. And after that, we need to evaluate to see everything is okay, convert it, and deploy that model in devices, in small devices like microcontrollers or even cell phones, for example. Is an example, or Raspberry Pis, etc. No, okay. So everything that we do with machine learning is start with the most important part. That's not the model, but it is the data. The first thing to do is data collection. Okay, perfect. So let's say what you can use, what kind of sensor we can use to do this data collection. No, as we saw yesterday in the presentation, we saw that for example, IMUs or gyroscopes and accelerometers can be a very good device or sensor to be used when you want to capture data to see how the motions are working or how transportation is going. Okay, so for example, when you have those devices, no, accelerometer or gyroscopes, what's that? Accelerometer is one sensor that, as Professor explained yesterday, and for example, you have internally, you can imagine you have two small, very same millimeters or nanomillimeters piece of metal with some kind of something more heavy, and that when you push something, when I do this with accelerometer, move the accelerometer, what's happened is that because the inertial thing, we move the space between the plates, and you can change a capacitance and change the capacitance. We can control that and see the change in an electrical signal. And at the end of the day, all sensors, as we saw yesterday, is something that converts physical stuff to electrical stuff in general. Would be passive, etc. But the point is, in this case, we can change movement or acceleration. We change this with accelerometer. We can have acceleration values converted to electro signal. We also have the gyroscope that's very useful in such kind of situation. In gyroscope, what we do is we can see movements, circulatory movements like this, for example. So in fact, for example, when you have it's very useful in airplanes, for example. No? When your airplane can accelerate in this situation, but the airplane can also roll. He can do a movement in this X, or he can do something like that. No, it's a pitch. No, he can, for example, do such kind of movement that's yaw. So in a space, together accelerometer and gyroscope can extract a lot of electrical signals related to the movement, horizontal acceleration, vertical acceleration, correct roll movement like this, all those stuff. So very good. So if I use something like this, I can take my container, okay, put a kind of a device in this container, correct? With, for example, those kind of device. In this case, only the accelerometer is very useful for normal operation. And you can do, for example, fantastic. If I put this accelerometer here and the accelerometer return back a signal that's going up and down, perfect. Probably I'm using my good is in a forklift. If it's more in a horizontal way, probably I'm in terrestrial path or rail path, no? And if you be something different, maybe it's in a boat. The boats are something more complicated. When you look at boats, we can imagine the situation. When we have such kind of a container, no, in a boat, no, we can imagine what's happened, no. The boat can go in straight line. The boat can do this kind of movement because the waves, no. The boat do this movement again because the waves, no. If you look in front of the book, they have this kind of movement. Usually, let's say the normal go to plus minus 30 degrees, but in some situations you can see 45 degrees, for example. Of course, I can do that. If you do that, we'll be in a lot of trouble. And more or less with the other situations also. This is good, no? So with such kind of device, we can do all of this. Okay, so let's concentrate in accelerometer, because the accelerometer is something that you can simulate easy in our laboratory today here, okay? Perfect. If you have it here, let's take a look what the accelerometer is. When you do this kind of movement, as I show here with the container, no? When we are moving the container here in some situation, as I said, this sensor will give electrical signal connected with the three axes that we have here, X, Y, and Z, okay? I can see, for example, suppose that I movement, for example, let's say that this is the X, suppose X, the X-axis, né? Okay, is this one, the red one. If I'm doing this kind of movement, you see a kind of a senoid here, a senoidal movement, correct? And if I'm doing only this and not moving in the Y or Z, we should have no signal. Of course, you said, but I'm seeing a kind of blue signal here in the ZX. That's correct. Even if I stop it or do nothing, I have the gravitational acceleration. It's 9.8 meters per second per square second. So even if you have an idle here, we have a vertical acceleration that you can see here. In fact, we'll filter. We'll talk about filtering. We'll filter this signal before we work in the model, because you don't need that. Okay, and also you see that, for example, this is a real case with this kind of a simulation that I'm doing here. So if I do this kind of movement, you say, well, but you are doing a cycle, I don't know, 1 second or 2 seconds, correct? In 1-2 seconds, I move my small container here. But we can see that also we have a lot of small movements or more higher frequency in those kind of movement. Yes, this is because, of course, I have, you know, my body electrical signals here that I move in my hand, something shake. I have some shake here. I have a influence from electrical signal that are here. So a lot of signals will influence in our sensor. So everything is there. And maybe I need to filter that. I can take this out because I'm not interested in such kind of thing. When I have for example, when I have a terrestrial, I'm maybe not interested with the movement of, the small movements that we have with the container, etc. Okay, perfect. So first thing that we need to do, if this is my signal or my raw data, this is the input that you need to take, like the signal that came from the microphone that Brian showed you last Tuesday. We need to take the data out of these guys. Oh, I said, not complicated, no? What I can do here is, for example, we go and take one point, because we have this signal is a continuous signal, is analogical signal, but we need to do a sample of that, including all our devices, be it our smartphone or be the Arduino or whatever sensor device that you have, sensor connected with the microprocessor. You do a sample. For example, in our example today, we use 62.5 hertz. That means that in 1 second we took 62.5 samples from the data. When you take one sample, what means 3 electrical signals that came from these 3 axes. So, for example, when I put here, I took these 3 signals. The idea, I go to the model, and the model should classify the first situation that we are interested. So let's go a little bit deeper. So what it means is, when I took that information, I need to take let's say, the voltage that is coming out from the sensor. So it could be, I don't know, minus, should be should be something, some value from the X value, because I'm doing horizontal movement in this example, something near to 0 in the vertical movement, for example, or the other X. But we also see here something around 9.8, that is the gravitational situation. Perfect. So the idea is, I took this data to my model, and my model will say, oh, you classify in the output like a tensor, no? Or a vector. That's a tensor with one dimension. That will be the first one, let's say, is a horizontal movement. The other is the lift. The other is maritime, the idle, blah, blah, blah. So my four classes. And I would like to classify, this signal comes from that. Well, of course, I know that only one point is not enough. So what I need to do, we need to take more dots. So the same thing. I mean, let's say slice continuously this kind of signal and take all those data, enter this in the model, and the model should say to me what class I'm talking about. Okay, perfect. So should this work? Not really. What's going on here is when you take one sample and use one sample, another sample, in fact, we are losing the information or the relationship between those points. Could be anything. This case is a continuous signal. So we call this in data science is time series data. It's something that's related with time. When we saw here, it's important. I have a cycle here that's repeat over time. There is a kind of situation. If you only took small points or values, this one point is not related with another. So I can't really create a model in a simple way. So what should do? Well, if it's a time series, I'm talking about some cyclical data, so let's do different. Let's take a window here. Let's say, looking the signal here, I'm looking, it's okay. If I do this kind of movement in my experience here, maybe if I put a window here, a few seconds, I can have some cycles and I can have some information here that's more meaningful regarding the data. It starts to make sense. But let's see how much data we are talking about. Remember, I told you this is a real data, and this came from a 62.5 hertz sample. What means that every second I have 62.5 points or data. If you have a let's say that I choose 2 seconds for this window. So this means that 125 points of data for each one of the axes. So we have in this case in total 375, let's say, features or data. Is my X, is my input. Remember saw the Monday with Lawrence, no? We have that's model. We have a lot of data enter in the first level here of my deep learning model. Okay. So this in general is not a lot of data, correct? Yes and no. But what's point is, we're talking about, and this is not a big frequency. I can have frequency much higher. So it's complicated. And if you take all the raw data, only converted the raw data, even using a kind of a window here, we have a lot of features, a lot of inputs. And remember, each one of these inputs should be related of one neuron, okay, in the input layer of my model, if I'm talking about a neural network. So it means a lot of computational complexity, and computational complexity means more memory. We saw this during all this week. So to solve this problem, okay, the way to solve this problem, when I have, we say, very noise or complex signal, like sound or like a signal that came from accelerometers, gyroscopes, or temperature. For example, you saw today with Matthew, a lot of, we have a lot of signal that came from atmosphere sensors. At the end of the day, it's the same. I have physical components that is translated to electrical signals, that the electrical signals will translate to, we digitalize them and translate this to data. And this data must be, treated before I really enter in the data in the model. We can do straight, but the model would be very, very complex. And at the end of the day, memory is one big restriction constraint that we have with the TinyML. At the end of the day, we must remember, we are talking about TinyML. We're talking about how we have real situations and put to run inside very small devices, okay? So what you can do? What you can do here is to pre-process the data. And how we can do pre-process the data? We can, for example, in this case, we can use one area that we call spectral analysis. Okay, the same we saw with Brian when he changed the sound signal to an image, né? Usando MFCC, it's a kind of algorithm to change. We'll do more or less the same here. So we call spectral analysis this kind of conversion. We'll talk here. Let's see what should do. First thing, okay. First thing is we're talking about Windows. Choose my data. Each sample of my data is 2 seconds. Is 2 seconds a window that I take from this signal. Okay, what should be done? First of thing, the most easy thing. I saw the RMS value, the root mean square. I mean, I have it here. 0, -2, -4, -6, blah, blah, blah. If I took all this signal and let's do only an average, sum everything and divide by the number of points, we have a problem because I have a positive and negative. So let's do different. Let's square each one of these values. We do that. We divide by the number of points, but because I square the value, I need to take the square root so I can return to the same dimension. Is meters per square second. That's it. This is root mean square. So with this window of 2 seconds, I can have 3 data points. 3 data points. One RMS value for each one of this. For example, in this case, will be something very positive, a number from the x-axis here, the red signal, and almost near to 0 to the other x. In this case, if you do the filter, the gravitational acceleration. So, very good, very good. And remember, we are talking about 125 is my n here because I have 2 seconds of 62.5 hertz. So it's 125 points. This is enough? Enough? No, it's not enough. I have here, I say a scalar value of how is the behavior. It's very important, but it's the behavior of the signal in this 2 seconds window. But this is this is a periodical signal. We go, you can see looking that go up and down, up and down. There is a kind of you look at this is a kind of a frequency. So how we work with frequency? The easiest thing to work with the frequency is to go to the frequency domain, or means take looking those kinds of signal and see how are the frequency components of that. Okay, let's people ask Tuesday about FFT, that is the algorithm that are used to extract the frequency from a time domain signal. So, for example, this is a real case. I went there. I took a signal. This is a noisy signal. When you look at that, okay, you can see, wow, this is a complex signal. How I can understand that? It's not easy only looking to understand in the time domain. But in fact, this signal, he can be, I can say, split in 2 very simple signals. For example, we are talking about two sinusoid signal. Okay, I'm telling you, for example, if you add 400 hertz, for example, component, it's for example, could be my voice here. My voice, I have components that go to 400 hertz, and here I have a second component. For example, it's 4 kilohertz, 4,000 hertz. That probably should be some kind of a noise that I'm not related with my voice here, because I'm talking, probably I'm not go to this high, but I don't want to go, at least, for example, no. And another important component when I talk about senoids or this kind of a periodical signal is not only the frequency, but also the peak, or the value of the peak or amplitude that I have here. So, for example, if you look at this wave, I can tell you guys, well, guys, this have one frequency of 400 hertz. I have, I don't know, 1 volt of amplitude here, and this another component. It's a 4 kilohertz of frequency with, for example, 0.3 volts of amplitude. If you add those components, we return to here. But in our case, this is what I have. So how I can have that? I can use, for example, FFT. I don't enter about the algorithm itself, okay? In fact, it's an area that I like it because I can say more than 30 years ago, I worked for Avibras Aerospace company in Brazil, and we used it. I programmed FFT in C in that time to analyze rockets. When rockets was launched, what happened with the vibration? So we used FFT in that time, but using by hand. Nowadays, it's only expression. You go to, for example, in Python for SciPy, you can from SciPy point FFT, import FFT. You say enter with the host signal here. I can plot the result, the YF here, and he'll show us, look, you have one component of 400 hertz. This is the amplitude, and this is another component with 4,000 hertz here with this amplitude. So I have algorithms implemented in every language, in C, in C++, in Python, any language that can do this very easily. And this is something that we do. And having that is easy. If I told you, guys, let filter, for example, I don't want this kind of noise here. What means filter is only coming here and take this component out. I don't want components over, I don't know, 1,000 hertz. Perfect. I come here and say, okay, everything that 1,000 hertz, I will take out. What happened? If you do this, you only have this component here. So it's very easy to do filtering. Take this raw signal and do a filter. Okay, perfect. Fantastic. Let's go. Let's continue. So having the window, I took the RMS. I came here. I took out the frequencies. And what we will do is having this the FFT signal, no, in the frequency domain. This is time domain in seconds. This is frequency domain in hertz. I say, let's take the 3 main peaks. Or this is a frequency of 1 hertz. This is a frequency of 3 hertz, 5 hertz. This is I have almost 6 meters per second. Here is the acceleration, papa. So I took from each one of the axes. I took the 3 main peaks and the 3 main frequencies. I have 3 peaks. I have 9 components. So my manual feature extraction now has 3 RMS, 3 amplitudes. 9 amplitudes, 3 per ax, and 9 frequency peaks. The main frequency. Fantastic. In general, this should be okay, but the specialists, like Brian said yesterday, the guys that study this kind of situation said, there is another thing that is power spectral density. That what means is you took your data or this window and you split in pieces. For example, let's take all the range of frequency between 0 and 0.5. 0.5 to 1 hertz, 1 hertz to 2 hertz, 2 hertz to 5 hertz. So, and look the power related to each one of the spaces, okay? And in this case, we have more four values, scalar values that are also part of my data. Times 3, because it's 3x, we have 12 here. So, from that raw data, that was hundreds of data points, in more than 300 in 2 seconds, I can reduce this to 3 RMS, 18 from FFT, from frequency, amplitude, and frequency values, and more PSD values. In total, we will have 33. We will have 33. Let's say a data set of 33 features. So our original 375 raw features, that was our raw data. Using spectral analyze here, I can convert this to 3 sets of 11 features, each one, so all equal, but related with each one of the X. You saw, interesting. So I reduced, let's say, 90% from more than 300 to only 33 data sets for that window. Of course, this is one data. This 33 will be one data related to this window. What you should do is to have windows each 2 seconds. In practice, you can have 2 seconds, plus 2 seconds, plus 2 seconds. I say windows that goes here one after another. But we can do something like a data augmentation here, because what will happen is if instead of go 2 seconds, 2 seconds, 2 seconds, I go, for example, each 500 milliseconds. So you have, in fact, I move this window to the half here, okay, to 100, 1 second here. No? Or 4 times, I mean. So we can, instead to move after the window, we will go one over the other. So we can repeat the data, but with this, I can get some situations that was not got if I took only one. So we only artificially, we are increasing the number of data there that I took in here. In our first example, we use 80 milliseconds, for example, for this sliding windows. This is what the specialist suggests, but you can change the values and depend of your sensor, depending of your case, this can be different. You can see how we can see that. Okay, perfect. So in summary here, we start with a 300, or we start in fact with a raw continuous signal that came from the sensor. We extract manually some data. We got 33 features from RMS, FFT, and PSD, and this will be the input of our classificator that will go to 4 classes. Perfect. So this is the next step is design the model. So let's a little bit more. And this is very important to give you an idea about the pre-process. So sorry about I took us too much here, but so
Marcelo,
yes.
May I interrupt you just a second? So before you get started with the second part, there were some questions, quite many of them, I mean, discussion in the chat about the Z, right? And you show the gravity value. You can see that in the chat. So people were asking, you know, some more explanation about that.
No, I mean, even we have the acceleration of gravity is a reality. So everything here is, you have, you know, a force, the gravity. If I take this container here and take my hands out, he falls down. And he was found down with a 9.8 milliseconds accelerations because the gravity. This value is not related with the analysis of the movement that I'm doing, for example, because I'm doing movements. In this case, our test with movements in terrestrial, rail, or ship, etc. So, for example, we can filter, take out that value to do our experience, because this value will be, doesn't matter what class I'm doing, all classes will have the influence of that value. So this is not good, because if you have this information is the same, it's not related to what I'm doing here, so let's take out, because it's only putting more burden in our analysis. I don't know if that was the question. We don't need it in this case, for example, because it's repeated. When you have data that's repeated and never seen, it's better to take out, because this is not will not help you with the classification, let's say.
And there was another question about the beams, the beam side, and you know, and also the sliding window. So
the beam is, when I took because I said I go to 0 to 2 seconds is the window that I have that I'm trying to analyze here, correct? The beans is I split these 2 seconds the 2 seconds I converted in a range of frequency, correct? And what you do here is, in fact, I'll decide. I'll say because I'm talking about movements that I'm doing. This is related to our experience that we do today. So these movements, and more or less related, we are talking about a real situation. In our order of hertz, we decide, okay, let's say that instead to have infinite, because when I took the FFT, he calculated the frequencies for me. I took the 3 more important. So let's do another thing. I know how the most important, but let's take this. I use a range of frequency and is split in four pieces. And each one of the pieces, I tried to calculate the power that frequency is related to us. It's a little bit is more or less the same explanation or the same use that Brian showed Tuesday. When you have the sound, he slice a piece of sound and try to see in that piece slice of frequency how the frequencies are, the influence of the frequencies in that specific piece of frequency, range of frequency. Okay, because of course I have infinite numbers of frequency here, but the idea is to have a piece of that and analyze the influence of all frequencies together in that component and so on and so on. Okay, I suggest that you enter this blog, a very good blog here. It's ndac.com. It's why the power spectral density PSD is the gold standard of vibration analysis. This is used a lot in aviation, in navy, in navigational system, etc. Because exactly explain why when you have analyzed for pieces or chunks of a frequency, is better to have more information than only FFT. In this case, we are having both. Okay, and the other question was about
the sliding window.
Yeah, the sliding window, because the point is you have okay, we decide because it's a time series and we do all analysis that we do at time series, we use windows. We could have, I took these 2 windows and from here I extract 33 data points. So we can have, let's say 0 to 2 seconds here. I can put another one here, 2 to 4 seconds, more 33, etc., etc., etc. So if I have, for example, 10 seconds of data, you could have 5 windows, correct? With 2 seconds for each one. But what I'm talking about is sliding. This is a sliding window. I took 2 plus 2 plus 2 plus 2. I'm using a 2 seconds or 2000 milliseconds of sliding window because I'm covering all your data. Suppose that you have 10 seconds of data. I'm covering that with 5 windows. But in reality, what we do, we move this fixed 2 seconds window. We change it in a value that we call this sliding window time. In this case, 80 milliseconds could be 100 milliseconds, 500 milliseconds. If you use, for example, 1000 milliseconds, what you have 10 windows, correct? One 1 second, another one. Remember, and we will have some kind of if I put here, I will have some windows will be one over the other here. Okay, perfect.
Excellent.
Okay. Well, let's continue here. Let me say have a. So we have the, now I have a lot of 33 feature samples, a lot, because I have this window moving here. I went in my neural network classificator and we'll get the classes. But what is this guy? This guy, for example, is something like this. You saw with Lawrence in the beginning of the week. So this will be, in this case, this easiest model that you can have here is we call dense neural network or full connected neural network. What means this complicated names? the model. No, this is the type of the type of the architecture of the neural network that I have. A DNN means that I have 33 features. What means I need to have in the input layer here 33 neurons. Each one of the neurons connect to each one of the 33 features. You have this is my start point. I know that I should have 4 neurons at the output. Why? Because I have 4 classes. I have lifted, terrestrial, maritime, the idle. I choose from the beginning. From the beginning, I choose my project to analyze these 4 classes. So I have 33 is the input, 4 is the output. The layers, the neural networks that you put in the middle, we call them hiding layers. How much you can use? 1, 0, 2, 10. You can see how much layers will be enough for you to do the classification. How much neurons you have in each one, you must see how there is a lot of techniques to try to help you with that. But at the end of the day, it's a try and error situation. How much neurons? I know the neurons of the input should be equal to the features, the number of neurons of the output connected with the number of classes, but the intermediary you can change. We'll see today in our exercise here. Okay, so this is the dense neural network or full connected neural network, because again, this is a real draw that I saw that I create. And when each one of the neurons are connected, this neuron here receiving a synapses from each one of the 33. So here 33, 33, 33, each one, this 20 is connected with each one of these 10. Each one of these 10 is connected with each one of the 4 final neurons here. So you can see it's a lot of connections. And remember what Brian told us and Lawrence Monday, these connections, in fact, is this, remember, it's the W's and the B's. Remember, returning to Lawrence the first day, when I saw the very simple example with, one neuron, we have a X as an input and a Y as an output. What we did, what the Lawrence showed us is how we calculate the weights, or how calculate the parameters, the W and the B, the bias. At the end of the day, in that case, it was a linear regression, and we know that the linear regression is Y equals to A or W X plus B is independent value that where the line will cross the YX. So I mean, at the end of the day, this is a complication. A lot of complication, a lot of neurons, a lot of connections, but each one of them is more or less the same as Lawrence showed us Monday. So what you do here is calculate the W's and the B's of each one of these neurons. Fantastic. So again, it's complicated to see all that connection. So let's put it in a more simple way. So we have the input features, and you have the input features here, and you have the output classes here. Okay, we have the input layers, 2 hiding layers, and the output layers. Okay, this is the thing that you should do project to here we are designing the model. After that, we need to train the model, correct? What I'm talking about is, okay, when I design the model, is another way to see this. Okay, I have the input layer with the 33 units. I have here a hiding one that received the 33, but he has 20 neurons. He's received the 20 data for each one of the input here, but have 10 and go to the output. And we have the activation function in each one of these cases. Usually with DNN, we use the head-phi linear unit in here in the hiding layers. This only means that if your data came from the previous layer and was negative, go 0. If it's positive, I copy the value from input to output. This is what it means with file linear unit. And the softmax here, what he'll do is like a sigmoid. Because I'm talking about classification and the number and the neurons will give a value in between 0 and 1. What you do is we'll use this activation in order that the last and more important neuron that's related with that class will have the biggest value. Okay, that's the situation. Fantastic. So those till now, all of this was theory, but it was important for you guys to understand. We need to collect data that we use. We'll do this using a sensor, the accelerometer. We need to preprocess the data using spectral analyze. Okay, that was convert the raw data that I came here, the 370 values in each one of the 2 seconds window. We converted this to 33 values. That will be the input for my model that I just designed. Okay, it's okay. Now it's time to what? To train, evaluate, deploy. It's a lot of work to do yet. I did, but I tell you, we did the most important thing so far. Now we need, to apply mechanism to help me to train that, etc., and to evaluate and deploy this in my endpoint device. The good news is that we saw this during this week. We have a package that help us a lot. TensorFlow from Google, for example, PyTorch from Facebook. There are Cafe. There is a lot of let's say functions or package in the market that can help us. I like a lot to use TensorFlow. It's very nice. It's very good because it's something that works in academia, works in the industry. It's the community that use this is a lot. It's an open source. You can use it in your projects, and you don't need to pay to use those kind of packages. But you need to know how to do that. The good thing, as we saw in my presentation 2 weeks ago, and with Brian Tuesday, the Edge Impulse is a kind of a tool that was designed for us engineers, to took data from the real world, pre-process the data, train a network, and make the deploy. So it's something that can help us to do that. And to do this, we will use Edge Impulse Studio. That's a kind of it's an embedded machine learning platform. It's kind of an auto machine learning platform. So they will guide us in all the process that should be done to create a trained model that can be used to do inference, that to be used to classify new data or data that we didn't knew before. That was our goal, correct? Perfect. So let's really start more real. We'll create a project to run our motion classification project with all those stuff using here our small container, correct? Perfect. First, we need to define, for our exercise here, we need to define what's the movement that we want to classify. So I decide. So we could use an Arduino. Okay, we can do this in the next seminar. But what we'll do now, in reality, what we'll do is we'll take a real cell phone, a mobile phone, okay? And let's say I will use the accelerometer sensor that are inside here, and we define the movements and capture data from this. So, for example, I will define the lift data. The lift data will be something like this. We simulate a forklift. So we simulate that small tool that put the cargo up and down in ports and storage, etc. So this will be my lift movement. Also, we define terrestrial movement is something left and right. So I'm simulating, let's say, what's going on with a truck or a train, for example, okay? So we go in this situation. And for maritime, it will be more complicated. I leave for you guys, but for example, what I did is, okay, I suppose that, as I said, I was in my boat here. So I did something like this. I did waves like this, okay? I did mix it with something like that, okay, a little bit something here. Or I mean, something more that means that the container is doing something more complex in the 3x, okay? That simulate what the boat is doing. Of course, you don't need a special container. You only do this with your phone up and down. Okay, I'm only suggesting these movements because for us to have the same experience. So this will be terrestrial or left and right. This will be the forklift, the lift that will be up and down, and and something like this will be the maritime one. And the most complex one will be the idle. I suppose that I'm doing nothing and my container is stopped. Okay, it's no movement. Could be inside in every. I don't know where he'll be, but could be something like that. Remember, I could also have a GPS connected. I can also have more information. Of course, I'm talking a very simple. I'm only using one sensor here. Okay, perfect. So what we do here is exactly what we took all the time till now. Is 40 minutes talking about the theory. What you do is take information from the sensor that you have here, okay? Perfect. We'll do is collect and test the data that we have, the data that we'll collect here in the cell phone using the accelerometer as a sensor that we have here, and you got that wave here, okay? For that, we use the edge impulse, okay? And remember, as an edge device, in the future, we'll do this using, for example, our kit, or you can use only a small device like this one. But only to remember you, what we're talking about, if I have a camera here, I have a camera in cellular. I have here the IMO here, the inertial inertial unit here that has accelerometer, gyro, and magnetometer that's related with GPS. And I also have this in the cell phone, and I have the mic here that I have also in here. In our example today, we use the accelerometer that you have the cell phone, including the data that we capture here. You can use this data in another device or Arduino that also has an IMO. That what you should do, of course, you see if the data that you capture here. I capture here data with 62.5 hertz. Okay, I capture data with the Arduino with 62.5 hertz, for example, to do the same path. Some could be the amplitude of the signal that is generated here is not the same that I generated here. But what we do, we can normalize this, put everything between 0 and 1. So I mean, so we can have filter. Let's say I will filter the data, I filter the signal that came here with the same level of filters that I use here. So all data captured with other devices can be used in a third device, taking the care that when everything that we do with a device A, you need to do with device B. Everything that you do to prepare the data for training should be the same that you do. Maybe let's say it's the different way to do that, because what we want is the same type of data as an input for our model, the same tensor using a deep learning nomenclature here. Okay, perfect. So the idea here is to create a project. Okay, let me go to. I think that all of you have the Edge Impulse Studio installed, correct? So what do you do? Go there and create a new project. Okay, you should create a new project here. okay? And give a name for that. Give a name for that, okay? You create a new project, the project will be here, okay? In my case, I have I'm using this project here, okay? And I took some data, but let's do a few together, and I give a little bit time. I will answer some questions in the time you guys are collecting data, okay? So the first thing, remember, when you create your project, you appear at a dashboard, okay, with the name of our project here, okay, perfect. Of course, here will be 0 because in your case, if you're starting now, it's not completed. Remember, some people asked for Brian, how I can reference the values of latence or use of memory for each microcontroller. If you go to the left, to the right, go down to the left, you have this project information here. Here, it's one label for data, I guess you have. Here, you can choose among several devices in order to give you reference. They will not be used for training or classification or whatever, only for reference. So, for example, if you put here Arduino Nano 33 BLT Sense blah blah blah, is exactly the sensor that we use in our kit here. Okay, and so let's do that. Arduino Nano 33 BLE Sense. So this is the guy that we use here. So all the values of latence and memory will be related with this guy in reference for us when you do the steps here. Perfect. So the first thing that should be done, we should connect a device. We need connect a device to capture data. So what we should do, we come here to the top, connect a new device. You connect a new device. When you do that, you have here, use your mobile phone, okay? You could, if you use Arduino, you come here and connect Arduino. You do this in the next seminars when we have the microcontroller. But today we use our mobile phone because we saw, the mobile phone has the same level of sensors that you have in our kit. So we have show QR code here. I open my phone. I open the camera. I'm pointing the camera. When I point the camera, appears at the top, appears a URL. I click it, and he's connecting with here, connect with Edge Impulse. So what means that look, he saw my telephone here is a mobile, is connected to accelerometer, microphone, camera, positional is the GPS. So it's green here. Means that my phone is connected now, okay? So once you have the device, is the start, we must capture data, is the first thing to do. So what should do now? We come here and should start sample something. So, okay, my phone is connected here. My sensor is accelerometer. You can check here. I have a microphone. With Brian, use the microphone. Here, I use the accelerometer, okay? And you need to give a name for that, okay? So, for example, let's say lift. One of that I did before. So, start sample, okay? So when I put here, I start to sample my lift movement, okay? I'm starting sample the lift movement, up and down, up and down, up and down, up and down, okay? Automatically is going up. Look, this is the guy here, and you can see here, okay? So the movements associate with this guy. In fact, doing here, up and down, is interesting because I have a wave here, no? I did a wave, but I have a level of 9.8 milliseconds per second. That's the gravity. I need to take this out. I will take this out when I show you guys there. Okay? So this one piece of information. Perfect. Now, let's do one for terrestrial. I think it's that, terrestrial. Okay, same thing. Let's start sample. Okay, I'm sample here, my terrestrial. Okay, remember I have a sensor inside. Okay, it's uploading here, terrestrial. Fantastic. Look, terrestrial is here. Okay, so this is like ZX. It's the ZX. I can see a movement in ZX. No, the XX is that one here. I didn't move in your direction. Okay, I'm moving left and right, and I continue to see the 9.8 milliseconds here because it's the gravitational. But I didn't did that, so I have this fixed value. Okay, let's do the same here. Look, my cell phone disconnected, so I lose here. It's very simple. What you do, you open again your phone. You're opening again your phone. Okay, it's not connected. Okay, so what should do is only refresh the browser. Only refresh the browser. Boom, it's connected again. So terrestrial. Let's move this to maritime. Okay, let's say maritime here. So I'll do my boat is doing a lot of movements here. It's the ocean is bad today, huh? Here. Okay. So we can see here we have movements in 3 axes here. So it's a lot of movements. Okay, and of course the idle. Let's let do the idle. Also the idle here. That's the idle. I have a idle. Sometimes I put 2 Ds. Don't. It's not a problem. No, I do that. Look, someone made this question to Brian Friday. I made a mistake here. I will put ADD double D. Okay, let's start sample. So now I have no movement. My container is stopped somewhere, waiting for something. Okay, perfect. So you can see here, we have not a lot of movements here. And I have again my gravitational acceleration here. But look, here in this panel, I have lift, I have maritime, I have idle, I have terrestrial, and appears a small one here. Oh, now I have five classes. I don't want that. I want only 4 classes. So is here, I came here to these dots here. I put here and said, edit label. Oh, wow, it's idle. Edit label, perfect. See, now I have perfect for classes here. Okay, your turn. Now is your time. So let's say, as Brian said, 10 minutes more or less for you guys to do that. I can answer some questions there. Okay. Let me return here only to show you. So the first thing we are talking is the data set, show the QR. We have in my presentation. Capture the QR codes. Okay. I put here in the presentation only for you guys. For example, I had problem with my for example, using this is iPhone 11, I have no problem. Using iPhone 6, the OS is not the last one. I needed to enter in the privacy and security settings and motion orientation access. And I need to give the access in the settings. Maybe it's the same with your phone. Sometimes you need to do that. If you have a problem, you should do that, okay? Pay attention with that, okay? So you should connect the cell phone. If you have a problem, as I showed on live, you need to come here, okay? And here you capture the information. You show you have the time appears here and in your device in this case, okay? So all the data that you capture, you can see here, okay? And one important thing, for example, when you capture your data set or your data, you be captured, let's say as a trained data, you are capturing is train. 100% of your data is trained data, okay? Perfect. What you should do, and remember, Brian explained very well this Tuesday. This trained data that you capture is our, let's say, original data set, okay? The first thing that you should do is split, or what means split? Save a few data to do tests after you train your model, because you don't want to mess with this data. This will be a new data, only to check your model at the end, okay? And you should do this before you start the training, okay? Because during the training, what you have split now as a training, okay? The edge impulse or the TensorFlow codes will split again in validation and training set. Why? Because in every time, in every loop in your training, every loop here, when you are training, you can use this validation data to check how your accuracy or your loss is going during the time you are doing the training, okay? When you are okay with that, your model is finished, you return here, took the test set that you didn't use for training, nobody touch that test data, and you use this test data to test your final model, okay? Perfect. And the next step will be, as Brian showed us, is the impulse, where you do that. Okay,
Marcelo,
time for questions.
I think there's two questions.
Yeah.
So the first one is, how many samples of every category should we take?
Yeah. Depend of the project. In this case, for example, I test for example, I use 10 seconds. Okay. I use 10 seconds of data, each one of 10 seconds. And what I did here, I did 1 minute, I start with 100 seconds, 10 samples of 10 seconds. Yeah.
Okay.
And after that, what I did, you can do two things. If you go to the dashboard here, when you have a lot of data, it's good you come in here and you have at the end of the first page, the dashboard, you can do here, perform train test split. Edge impulse will do automatically for you, like 80%, 10%. You split the data for you. In some cases, worked. I did here, for example, and the split was not so good. So, for example, when you have control, I'm not talking about the thousands of data, okay? What you can do here in data acquisition, what I did is, I came here, look, I have filtered your data. I can filter. For example, I came here, let's only have the idle here. For example, what I did is, I come here, for example, I took this idle here, for example, I came here and moved to test set. Do you want to move to test set? Yes. Okay, I moved that. Okay. Let's say today, for example, I have for example, the maritime that I did today. Okay, boom, I can move to test set. For example, I move to test set. Let's come to terrestrial. When I put here, he's showing all the terrestrial. I said, okay, this is today. I put, when I have the data, including, I said, well, let's take, I don't know, the second one or the first one. I took, I think, 20 seconds of each one. I have 10, so I ended with 8 seconds and 2 seconds. So move to test set. Yes. Okay. Well, if you are doing the last one was lift, I did today. Lift, this is today. I also move to test set. Yes, move. Fantastic. Okay, here, let's clear the filters. Okay. Now I have 33% of train, 27 for test, because remember, it was 80-20, because and you can see here, when you go to test set, I have here, okay, so in this case, I have 20 seconds of each one. Was 20 before, now because I put one more, was, so it's more or less. Depend of you, okay? You could leave there, but answer the question, Marco. There are more questions?
Yeah. Yes, I'm replying to some of them. So one was asking if you can import, other data like voltage and current in a different way. And I said yes, through CSV files.
Yes, right? That's it. Yes. When you have here data acquisition, if you came in here, is upload the existing data. If you come in here, I'll show you something. If you have, I see that you have, no, I don't, I'll try to have time today. You come here, choose files, you come here. When you choose the files, you open your computer, you come here, you choose the files that you have. For example, you can have here, for example, CSV files, you can have wave files for sounds, you can have JPG for image, you can or PNG. So you can list and go up and put up. Okay. Only take care. Maybe we can do this in this kind of exercise when we do some next workshops. You must, for example, I would like to capture data that because this will be a reality. I like this question because when you have your sensor in the field, you took the data. For example, we did this for example, a lot of people saw our students that University did the ECG, for example. They captured data of a real ECG, but they went, took the data, captured the data, and they did that. They put the data in a CSV file, each line, which one of the samples, in our case here, will be with 33 columns, correct? 33 columns. And the number of samples, and the line is the number of samples that you have. And you should have a column that they call timeline, because you should tell the frequency that you are capturing, and the top, in the top, the name of your label, or the label of your data that you are capturing, the raw data. For example, in this case, it will be ACCX, ACCY. That was the name. If you want to use the same, you need to use the same, so you can mix all the data together, for example. Okay. Let me launch here a question to have an idea here. For you guys, tell me if you already did the data collection or not. Wow. Fantastic. I don't know if you guys are seeing, but let me push, if I put it here. No, it's not sure. Oh, I have a 78%, 230 already did it. I think that you need. Let's continue.
Marcelo, maybe can you have a few more minutes just for?
Yeah. Okay.
Yeah, there were some comments about working on it. And
guys, as Brian explained to us Tuesday, I mean, with the pre-survey, we know we have people from everywhere in the world. We have here engineering students, and you have some PhDs. So for some one of you guys will be, my explanation is very weak and very slow. For others, maybe it's fast, is a little bit complicated, people that are starting engineering course, for example. But I'm trying to do at the middle, not to be very complex, but give you at least where you can find things, what you're talking about. Because, it's important for engineers, for people that work with scientific use of that, to understand really what's going on. Because, okay, tools like Edge Impulse are fantastic. They help us, they guide us, but you must understand what's going on under the hood, because with that, you can change things. You can use your, or do your situation, okay? I think that we have only 40 minutes to do. Let's go, Michael, now?
Yeah, sure.
Okay, so let's end this poll here, okay? I think that the great majority ended, so I think it's okay. Fantastic. I think now will be more quickly, because in fact we lose a lot of time with the previous discussion that will help us, because now it's time to do the pre-preparation. So okay, let's return to our project, okay? So we just finished the data acquisition, correct? So I hope that you guys have something like this. In my case, I have 5 minutes here, okay, of data, okay? And I have split here 80, 20, something like. In this case, I'll change a little bit. Fantastic. Guys, the next step is to go to the impulse design, okay? What means impulse design? Impulse design will be, you define inside the Edge Impulse what should be done. So, okay, perfect. Look, what do? I want time series data that use accelerometer that we did before. Our window size will be 2 seconds. With a windows increase 80 milliseconds, you can change this, test what's going on. And here's the frequency 62.5. This came automatically because he received from the cell phone, and they put here. In fact, Edge Impulse start giving you this. This is the starting point. That's the good thing. You can start with the phone, and including you do this here today, but you can change to see, because depend of your project, maybe you need to change. Okay. After that, we need to do the spectral analysis. So we only tell them, oh, you do the spectral analysis. What will you do? You enter with the three raw values from the axis, and the output of that will be 4 features: idle, lift, arrhythmia, and terrestrial. Okay, that we'll use here to our neural network. And this will, when you save, you have the impulse. So return here, impulse design. Okay, impulse design. Okay, you come here. Let's say, you take out this. When you open here, you have 2 possibilities: time series data or image, because they receive a data, they don't know what's could be the data came from an image. They don't know. No. I want time series data. And look the star here. He's suggesting us to do that. Perfect. The second one here, when you open the here, you have several possibilities. Could be a spectral analysis, could be flattening, could be image, could be MFCC that you use with Brian. You can use raw data. This is very important. That example that my students did at Unify with the heart, what they did, they captured data for a data set. They process the data by themselves in a more complex way, because they need to get the peaks of the heartbeat, blah, blah, blah. So they filtered, did everything, and they got the data set was a bunch of heartbeats, 1D image of heartbeats. You saw the guys that was in the 2 weeks in the 2 weeks ago presentation. Marco showed a video that our students did. So with that, they use raw data. So in fact, they use a raw data, and the window was the size that was, in that case, the windows was 100, because it was the size of the data. We don't need slicing, nothing. That was the input. And we decided to do nothing, is pre-processed. We enter straight to the neural network. In this case, we use spectral analyze. Including the Edge Impulse told us, it's great to analyze repetitive motion, is our case, such as data from accelerometers, extract the frequency and power characteristics of the signal, blah, blah, blah. Again, they start here. Okay, so you put add, is here. So perfect. When you have this, you can save the impulse and you have the impulse. I don't do that not to lose time because our constraint. Guys, when you come here, the next, what we did here is we only define what should be done. We defined that we took the data, we have the windows, we took slide the windows, we will use this, but he did nothing yet. So when you come here, for example, let me take one here. Amarito, for example, this is a, look, what I have here, this is the windows. Look, this is the windows, the 2 seconds windows. Okay, I'm sliding the 2 seconds here, okay, over the 10 seconds sample. Each time that I do this, we can see here the clean signal, okay, the FFT signal, and the spectral power signal. And look at the look one thing here. No, for example, in this part here, we have a default data that edge impulse is suggesting us. As Brian said, if you are not a specialist on that, let's use what they are suggesting and see if it works for you. So otherwise, you need to use some specialists to help you. But for example, I have here a filter. For example, I have, remember, scale X1. This is good because I can mix it several different sensors and with the same scale. Filter, for example, and I don't want filter here. Look, if you don't want a filter, exactly the signal that came from here will appear here. So it's very bad, correct? So now it's good. Let's use a filter. I think it's good. But what kind of filter? Low filter, high filter? No, I want a low filter because I want low frequencies only to pass. Because this something very nervous here is higher frequency. Remember the FFT example that I give to you, 4,000 hertz and 400 hertz. So this is, let's say, remember, like the small amplitude. I have a small amplitude of some higher frequencies. I said I want a low frequency. The cutoff, I use 3 hertz. You can use 5, 10. What do you want? They suggest 3. This is the order of the filter. It's more complex. And here the number of points that you use in your FFT should be power of 2, but you can put more complex FFT. It will take more time to do the analysis. Sometimes help, sometimes not. Okay. Here's the peak threshold, and here's the power edge that the pieces, the chunk pieces that from the frequency. So we choose 0 to 0.1, 0.1 to 0.5 hertz, 0.5 to 5. So are the 4 pieces to calculate the spectral power. Okay. If you guys come in here and copy this here, copy to clipboard and put in anywhere you want, you see you have the 375 values because it's all the dots, the 125 dots per dot data per X. But if you come here, processed feature, if you copy here, you'll find 33 number values. Fantastic. And again, and look, to do this job, an Arduino 33 BLT Sense that use a Cortex M4 will use 4 milliseconds to do this job in 5 kilobytes of memory. Fantastic. Our small device here has 256K of RAM memory, and so and then 8 milliseconds is okay. Okay, and of course, in reality, it will be faster than that because we're using a cell phone that uses a Cortex A. Okay, fantastic. When you save the parameters, if you are okay with that, and you go to generate features, okay? When you generate features, what do you do? Here you have our original 5 minutes and 22 seconds. That was the raw data, okay? Because I use a slide windows of 8 milliseconds, look, I ended with 3,230 samples, what's very good, correct? When I generate the features, what we do, we do a dimension reduction using a UMAP. So doing that, I can come here and I can, remember this, each one of our data, they have 33 dimensions, 33 features, okay? Lawrence showed you in the first week one example with 2 dimensions. Remember, Y and X was, with a very few points. So it's when you plot this is a straight line. With 3, it's good. I can see in a space, but I'm talking here a 33-dimensional space. It's impossible to design them. Maybe Einstein can see that. I can't see that. With 3, I have problems sometimes. So 3 is the most that we can really analyze. We can use 4, but the splitting in a few of 3s. But the good thing is, for example, we have here all the data, and I would like to see the RMS values between how they say, well, it's very good. Of course, when you look at the terrestrial, we use the most majority was in the X and in the Y-X. No, I have here the lift. Yeah, you can see it's the lift is here in the Z, correct? The maritime is complicated. I have maritime in the 3X here. Okay, so it's more complicated. You can choose other things. I can say I would like to see. Let me see. The peak of the first frequency connected with the spectral here, for example. So it's another thing. You can check if it makes sense for you or not. But the good thing is you can choose to analyze if you are a specialist in that to see if it's okay or not. In our case, I'm not a specialist. I like very much the RMS. I think it's included the suggestion. This is Y, no? Y. X, Y, and Z. I think that's good. When you do that, and you can see visually a separation between your data, it's a good indication that you can get a good classification here. Okay, so fantastic. If you want to analyze each one of these data here, you can click you click the data, and the data will appear here. This is a label maritime. It's this piece, this window from this complete data here. Fantastic. So again here. So once you have now the data is processed, let me launch here. If the people finish the pre-processing.
So in the meantime, while they finish the pre-processing, and this is great, Marcelo, there are, well, a couple of questions that were all replied. There was only one that said, with the up-down movement, it is not very well classified, while the right and left is predicted very well. So does that depend on how you collect the data? How?
Oh yeah, yes, it could be, but maybe when you put this, for example, maybe you did a movement in other necks, for example. But again, it's your data. Maybe you need to reproduce more data, increase the number of input data, and maybe the model that we use. Because I'm supposed that you went down to the model, we didn't went there yet. Maybe the model should be a little bit more complex. We need to make more layers, etc. Okay.
And the second one is, in which cases we use a high filter?
If you're having, for example, in that case that we are discussing about the hurt, for example, we don't want, for example, 1 hertz, for example, that's something like related to the movement of the body. So, for example, I will filter all my data. I can't remember the number exactly. The students comment in the presentation, I think 1 or 2 hertz. So I don't want 1 2 Hz before the 1 2 Hz. I want over 2 Hz, for example, 2 before 60 Hz. I don't want 6 Hz and over, because the hertz, there is not something like that. But I want another piece. Depend of your data. Depend what you want. Depend your project.
And connected to that, there was a question from Jairo, which was about including data in inputs for infrasound. So 0.1 Hertz to 4 Hertz. So really
I'm sorry.
The question, I think, had to do with very special data. So from infrasound. So very low frequency.
Infrasound. Okay.
Yeah. So if edge inputs can work with that data.
The data that we are using here is a very low frequency. I'm talking about 3 Hertz, 2 Hertz, 4 Hertz. We saw here, no? When you come here for the parameters, when you look, for example, here, when you go to the frequency domain, look, for example, it's 1 Hertz here. And of course, it's related to this movement. So we're talking about 1 Hertz, 1 2 Hertz wave. Could be sound in this, doesn't matter. At the end of the day, it will be numbers. Okay, you have your data. If you have a sensor that capture such kind of data, you can use it. Okay.
Okay. So we have 30 more minutes to go through the exercise. Will we be able to do that?
Sorry?
We have 30 minutes just to give,
Yeah. So let's go. Yeah. So the next step is to classifier what we did here. Okay. So let's end the pool. I think the great majority it's okay. Now, when you enter here, we can for example, we decide 20 neurons, 10 neurons, because I said before, this was automatically, look, this came automatically. 33 was the input. 4 features was the output. You said, that, for example, the example that you comment, I didn't classify very well. Okay, I can, for example, enter an extra layer here. Let's say, I don't know, another dense layer here with, I don't know, more 10 neurons. Now I have 20, 10, 10, for example. I have 3 layers. Maybe let's come here and, I use, I don't know, 30 neurons in the first. So you can, there is some tools like a Keras Turner that you can use outside to see, to test what is good to do. Also, we can see here. But at the end, so I don't want this. Let me keep only 2. So you choose what you want here. Okay. Now use here. You only to remember. Only to remember. Those layers here is related what we have discussed before. Each one of this is the input layer with the number of neurons here. These are the two hidden, and this is the end one, softmax, etc. here. Okay, perfect. So return to the classifier here. Perfect. So when you start the training, he'll do the training. You take a little bit of time. I see that people are doing now, correct? I will leave you open here only to have an idea. Training. Only for people to tell me if they finish or not. And you do the training. For example, in my case here, I got 99.5%. What's very good. Yeah, I can see here in the confusion matrix, I can see, for example, 99% of the idle was considered idle. You have some problem here. For example, some of them I made a confusion here. Why? I can see here. I can see, for example, let me see here. Here, I can see this one here, for example. Let me see what's going on. Look. This was idle, but look, in the last window, when I took the data, I was here and I move my hands before I finish the capturing the data. And of course, so I have a lot of movements in the sensors here, and he was interpreted as terrestrial because it's more connected with the YX. You can do, for example, you take this piece and delete it or put again somewhere as training again. It's your choice, okay? Important, the time of inference 1 millisecond, very quickly, a peak of 1.7, perfect here. So our device can handle that, okay? Perfect, great majority is it's done. Okay, well, some questions related how we can make the things here. If you come here, as Impulse launch a new thing, they call Ion Turner. Okay, you can come here if you want, and you can. It's auto machine learning. You can say, you know, I'm using Arduino 33. I know that these are the limitations. It's 256 kilobytes of RAM. Is 1 megabyte of flash. Okay, and so I'm work with continuous motion. So what do you want? I ask what AddImpulse do. He starts to change hyperparameters and do the test for us. For example, he said, wow, look, when you look at the result here, he said, for example, if you use a window of 2 seconds of window, but a slide windows of 1 second, you use, for example, 80 neurons in the first layer and 40 in the second, and you use a dropout because you turn off some of them to prevent overfitting. Look, and they use a FFT, not 128 but 1024. Oh, you can have a 100%, of course, because the FFT you take 56 milliseconds, no, to do the DSP. We did the 8 milliseconds before. So, okay, maybe if this is enough for you, you can do a bigger model, okay, more complex, a more complex model, a more complex pre-processing, but you can have a little bit higher accuracy. In this case, I'm selecting accuracy. You can select run, ROM, etc. In this case, I was selecting accuracy, okay? And that's it. And you can see here a lot of different combinations. So AddImpulse can help us, depend of your target, he can give you some ideas about what you want. And if you choose, you can select here. And because he tested that. I did a test before in my home because it took hours to do that, hours. And because he'll try to depend of the size of your data, you try a lot of things. You can do this now or after we finish here. And if you press the best one, you see that everything changed. Okay, perfect. Guys, the next thing you can do is live classification. Okay, I think that I leave this for the next section, but it's important to do the model testing. Remember, because we did because we have data that put apart for test, we need to do the test. I will ask classification, classify all, and what we do now is testing all the data again. Okay, and including we have some test data I did some time before. We took some of today, I put there, so I did again. He's doing now is inference. He took the model that was trained, is entered the data, all the data that we have. So we got 98.45. Here you can see some of the errors that we have. You can work with that. Okay, perfect. The one thing that I leave for you guys to do, because I would like to move on quickly. We did the tests here, correct? I show you. The next thing that you can do is test your model, do inference here. It's very simple. It's the same that we did with Brian. you can go to connect your phone, okay? You can switch to classification mode, and you can, simulate the movements, and you can see that automatically the cell phone in the cell phone you see the different movements here. Okay, so this is everything that we did today. Let's move on for the last part in 10 minutes here. We'll talk about anomaly detection. I think it's important. The theory I go very briefly. Okay, what means anomaly detection? For example, suppose that each one of these dots that we are seeing here is one of the data that you saw in that display there. Okay. In general, for example, what's happening here? When you look, look, this data is very, very close. This is very close. What we're talking about is those guys here are clusters of data that is more or less together. They should be related to the same class or the same situation. Okay. They should, for example, suppose this is the lift, this is the maritime, for example. But some of the dots, some of the data could be completely different. We are talking about, remember, here I'm looking 2 dimensions, but suppose that the data came from our example here with 33 dimensions. When you see the 33 dimensions, you can see, but when you use the techniques to reduce the dimensionality to 2 or 3x, you can visually see, or you can use techniques to do that. Fantastic. This is very useful when you work with machinery. For example, suppose that you have a factory, and each one of your machine have several bearings. Each bearing, for example, with accelerometers. Okay, what we're talking about here is the same thing that we did today. Each machine has these accelerometers. We have data there. But the point is, now I'm talking about higher frequency of a sample. For example, 20 kilohertz. I sample a lot. So if I have, suppose that we have one machine with 8 bearings, with 8 accelerometers, we have a lot of data that's connected every second. If I want to send this data for somewhere to analyze, it's very complicated. So this is one thing that you can do exactly with TinyML. We can put the brain together with the sensors, exactly what we did today, correct? What we do that? Windows, slide windows, pre-process, training the model. What I can have here? Well, if I do this in this way, what I'm training? I'm training working well or working bad. It's not so easy, because working well, I can have machine working well. But how about bad? What means bad? Remember, if you're talking about machine learning, supervised machine learning, when I said this is terrestrial, I did the movement, capture the data, and I write, this is terrestrial, this is lift. If I'm trying to see if the machine is working well, I don't have that. So it's complicated. So, for example, I have machine working well in one situation, velocity, tal. Machine is working well in something. But when machine is not working, can be anything. It's difficult to know that. If I think about our example, no? If I have, for example, here is the lift, here's the maritime, okay? What could be an outlier? Oops, could be something like that. Suppose that not our container went out of the chip. No, it's here, go out of the chip. We train it, for example, in a movement like that. We did a movement like this, and the containers can go down. Correct? So for that, I can use another algorithm that in fact is not deep learning. It's a simple algorithm that we call k-means. K-means. What this algorithm does, you look all the data, try to concentrate all the samples around a common point, let's say, a common center point. and they calculate the distance from those guys. And if they in a reasonable distance from a special center, oh, this belongs, okay, this is, all this green is one class, this triangles is the center. So we can automatically classify that. We can do this exactly the same way with edge impulse. What do you do? We do the spectral analysis. We did it, okay? But when we enter with classifier here, we can use in parallel another model. I have the data. One model was used. We classified five classes here, and I use another model to classify another situation. We call anomaly. Okay, so we should come in here again to impulse design. Okay, I have my data. The data is there. We train this guy. I said I would like to add another block here. I use classification keras. I would like to add anomaly detection. I enter anomaly detection here. Okay, you can see here I have now 5. Save impulse. Okay, now I have another line here. Another option here is anomaly detection. I must go here and decide. I would like to check. First of all, I will have here how much clusters we want. In principle, you can say, I have 4. We have 4 data. But it's interesting. They suggest much more depth. So they will have a smaller, he'll put all the situations, doesn't matter, because he doesn't know that we are talking about 4 classes. So the system will do is put 32 of them. Okay, I said, let's try to use all the RMS values, okay? And I will start training, okay? When you start training, what they will do, they will use K-means and calculate. Look, they calculate 32 areas around our data. Perfect. If I do something that's outside of this model should detect. Let's try to do that. Let's try. Let's use now a live classification. Okay. First of all, let me put again the device here, because I wanted to be sure, because we changed. So I will delete here. It's finishing, Marco. Connect a new device. Show a QR here. So let's see here. Camera here. I'm capturing here. Get start. Live classification. Perfect. What do you do now? I will start sample, okay? But I will simulate my container going to, is rolling out of the chip, for example, and going down. I'm rolling my container. Cross finger. Yes. Look, what's happened is great majority of the dots went outside of the area. Look here. I have all our data here. Okay, the leaf, the eye, the blah, 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 blah. And those are the guys that the samples that I took today at this moment. And they will appear here. So we can see that 98% or 98, when I wrote 98 guys was considered anomaly. Important. And what's happened, our classifier is the same. Look, for example, this is, he sought 81%, he said it's a maritime, and 19 is a lift. You know, another situation, they say, this is a lift. But it was not a lift. So this is very important. So now I have 5 classes. If the anomaly is 0, I can see all the classification. If anomaly is 1, if something strange happens, and we need not consider the classification from here. So this is a real situation where when we could, when I did that in a situation that the container falls down, we have this kind here. Guys, in the last minute, this presentation was done by Jan from EdImpulse this week in the TinyML Foundation, talking about projects in Africa. And I saw one of the projects did by Dr. Sirava Maina from Kenya. What he is doing, he's putting a accelerometer and a microprocessor, like this external accelerometer and a microprocessor, okay, in calls. And what he's doing, training when the call is moving, horizontal, when it's eating. And with this kind of work, with a similar project that we did today, he's studying if the calls are doing well or not doing well. And he can put this with a battery that can a lot of duration. So it's very, very, very good. Okay. I leave for you guys a project with division. I not talk today because, but it's a project that I did with my students when we took a data set from Uganda, that they are studying problems with beans. So you have a rust bean here is a disease here, problems, okay? But the point that problem that we have very few data. We have only 400 photos took from cell phones. So we have we did this. We have two situations to better do this. Data augmentation, we can took this, each one of the images and change the image and open down, and TensorFlow does this for us, and also TensorFlow EdImpulse does this under the hood. Yesterday, Mark showed you guys transfer learning. Remember, he showed us today yesterday, and we can do the same with this kind of projects. Okay, so you can go look at my presentation. You can have this project is public. You can clone the project. Okay, you can go when you open. You have a button. When you open this address, clone the project, and you receive in your account all the data that I put up. I use manually. I up JPG data. Okay, and you can see the results. But the good thing is, I left for the Eon Turner to show what should be done. And the Turner said to me, look, your image originally is 224 to 224 pixels. You should cut for 100 to 100 and use a transfer learning, is MobileNet V2, blah, blah, blah. You have 92%. So I did that, okay? I did what they recommend. Look, the data augmentation is here automatically. You can enter here and analyze what he have done. We did this, okay, and we can do the same. You can classify. You can open a image in your computer, and you can see and check. Marco, 3 minutes late.
No, it's perfectly fine. Super, super, super interesting. Just as I mean, first of all, thank you, and let's clap our hands.
Thank you, guys.
It was a fantastic presentation. And just as a reminder, I mean, the slides are openly available. So if you want to go through the exercise, later, you can do that. And it's a step-by-step, thanks to, Marcelo's ability of explaining things super clearly. Just a comment. I remember a couple of years ago, we had a case study presentation about a similar project for the cows, but that was before the age of TinyML. So this guy was from Peru, if I'm not wrong. And he was sending data from an IoT device through Zigbee to a receiver, and then that would go to a computer. So my point is that in that case, the battery would not last that long, and you wouldn't have the data immediately categorized, or the anomalies found. So this is a
very good point,
really a game changer. Okay. Let me see. So there's some questions if you want to check them in the chat, Marcelo.
Let me see if I can enter in the chat. I don't know because this appear here.
Okay, there was one question about what can Edge Impulse do.
I stop share. It's here. Stop share.
So one question is, what is Edge Impulse adding as a value compared to doing things, manually?
Well, first of all, a kind of guidance. This is very good. Again, this is a device. This is a tool developed for engineers. Okay, so if you are a deep learning specialist, of course you can use TensorFlow and everything. But the point is, including the last, if you are a data scientist, to do the last mile, that was take the model, shrink the model using TensorFlow Micro, something that you learn tomorrow with the father of this Pete Warden. It's very complicated. And what TensorFlow, what Edge Impulse does for us is when you test everything, the model will be shrink in a simple library that you can download and run in this library is straight in your Arduino or your microcontroller. Okay, in the Discord, I give you some examples that I did. For example, including with Pico. Was interesting because this was not supported in that time when Raspberry launched this microprocessor, and you can do everything, and they deliver to us a C++ package like Brian comment Tuesday, and with this library you can of course you must be an embedded engineer to know how to do that, and you can because they put. What they do, they give us all the libraries, they give the model, and they said, guys, this is the input, enter the tensor with the input, and they give us the output. That's it what they do. They gave us. And after that, we are engineers, can do all the project, took the data, clean, blah, blah, blah. So it's very good. Everything that this Edge Impulse Studio is free, is made for developers. Of course, you have a limitation of the number of data that you enter and the time to use. Big projects, you can go, you must use, they have, of course, a professional area when they make money. But I can tell you, and they are proud to say 99% of their projects are free. People use it as a proof of concept. People do to make developments. So I think Edge Impulse was I used to say, I remember I participated a few months ago in a presentation with them, and I told them, guys, Edge Impulse is doing for TinyML what Arduino did for embedded engineering 5 years ago. Everything became when Marco and I'm older than Marco. I learned in microcontrollers during the 80s, at the beginning of the 80s at the university. Was very complicated and not a lot of development to do everything is assembly. With Arduino, 5 years ago, I started to work with Arduino. It's very simple to do. And Edge Impulse is doing that for machine learning, for deep learning. That's I think the best value of Edge Impulse.
Marcelo, so people are asking, what are the limitations with the free account of Edge Impulse?
I don't know, but I mean, I never reached that. I mean, all projects that I did a proof of concept, all my data was accepted. For example, I knew Marco has one of your students, from Africa that was working with. I think that was the sound
radiation?
of mosquitoes. No, sound of mosquitoes. Yeah. And he had a problem, and he had a problem. He told me because it's so many data that was not possible to use in the. But it was the only case that I heard about that. We did together. I helped them, and we worked with the radiation and work it. We did work in university with sound, with the COVID, with the real data, and work it. This project with Hurt, we use real data, 10,000 of data, and it worked very well. And the model we developed outside was a big and complex model, and we entered with the model, and everything worked. We only used the Edge Impulse to capture the final model that was helped us a lot.
Okay. And then they ask about the generated library and if the interface is also auto-documented.
Yes, very well documented, very well documented. They generate, for example, when you generate a library for Arduino, for example, the code that are in the loop is very simple. It's take the data, take your data, put in here, because they give you an example. They said, for example, remember when I show you guys, take the raw data from that, make that copy, you paste there, and you can run. And they package everything. You can open, of course, in the library and see everything that they have done with the TensorFlow Micro. I can told you guys, I did when the Arduino, when Raspberry launched this guy, it was completely not supported, and I could connect to the device, capture the data, okay, and also I up data with a CSV, did all the job. They give a generic C++ library. I need to work with that library. I put in the Discord the link, and it worked perfectly. So Edge Impulse has everything very, very well documented. And remember, Brian told Tuesday, including, look, we use this spectral analysis. We use what was available there. But for example, suppose that you have a special filter that you need. For example, in our case, for the hurt, we use filters, but we filter before to enter the data. But I could, for example, develop my filter in Python, the same that we did for training our data using Jupyter Notebook. But we can use that filter, and they explain to us how to do that, to upload to Edge Impulse and use our block, let's say, to do that. You can do that.
Okay, super. So I think Matthew is here. So we have room for one more question. Final one, asking if you reach the data limit on Edge Impulse, in which other ways you can transfer the algorithm to the TinyML kit, or to some hardware?
No, okay. What should do is go to the traditional situation. What's the traditional situation? You use the TensorFlow normal to train your model. After that, you must go to TensorFlow Lite, that will be converted the model to a small model. That model should be converted to a flat buffer, in a kind of a buffer where the model is converted to x decimal points, and this buffer is the model that should be used in your model. You must, for example, use the start. My suggestion: start from examples that TensorFlow Lite Micro will give you. If you Google TensorFlow Lite Micro, you have some examples for Arduino, for example, that including running in this kind of Arduino. You find there, for example, the projects that Brian showed us the Tuesday, that was yes and no. So you see all the steps that are done, including the last part. Okay, with Arduino. I mean, so again, in short, is using the normal tools from TensorFlow. There are other libraries that also can do the job. Okay, but the most complete and the most supported libraries for TensorFlow Lite Micro, or for embedded devices, is the TensorFlow Lite Micro developed by Pete Warden, or lead by Pete Warden in the Google.
Okay. In fact, we're going to have the final keynote tomorrow by Pete Warden. So he's the father
and for example, if you guys, Brian comment with you and VJ, the excellent professional specialization that you have in EDX, for example, that specialization, they show the keyword spotting project. They show movement. They call a magic window with accelerometer and gyroscope, and some projects with vision. Okay, and they only use TensorFlow Lite Micro. And Professor Vijay entered in very detail all the bits and pieces that was used for those three areas. If your project is different, of course, you must adapt, but it's an example. For example, the EDX course doesn't use, or at least at the beginning of the year when they did it, didn't use it, EdImpulse. EdImpulse is a very new tool. It's a kind of auto machine learning, again, to help embedded engineers to do proof of concept.
Super, fantastic. So let me clap the hands again. The comments in the chat are really, say superb presentation. Everyone is super excited.